Okay, so we will begin. So, I already told you that is there are many problems that are two dimensional in nature in real life, and plane strain was one. I have given you the basic equations. Finally, you please derive the equilibrium equations for plane strain in terms of displacement. You add at the end of the lecture, I mean at the end of the notes that I have given you, you kindly derive the equilibrium equations. How many equilibrium equations there are there? There are only two. There are only two equilibrium equations. I think I gave you. So that one will be in terms of u and v. What are the equations in terms of u and v? So it will be coupled differential equation, which will be two dimensional in nature, not three dimensional, but two dimensional. All quantity u and v are varying with, and that will form the displacement method, because that will be the starting point for any displacement method. I have also told you that there are three approaches for solution of any problem: displacement, stress, and mixed. Of the three, displacement method is the most popular. There are many advantages of displacement method. One is that we start with the field, displacement field. We don't have to use compatibility. You don't have to, because the field that we assume that it is a compatible field. So, and then we understand our displacement assumptions. So, it is displacement approach is the one which is used throughout the world extensively. So, the starting point will be always your equilibrium equations in terms of displacement. So, please derive and put it in your notes, what are the equations in displacement method. Now, then I told you that there are two kinds of plane problems, two kinds. One kind we have discussed. So, the other kind is called, and this kind occurs in plane problem like dam, where the plane, and also in axisymmetric solid problem. Wherever you have axisymmetric solid subjected to axisymmetric load, anything that you rotate, any plane can be triangular, it can be anything, any curved plane, you rotate about this axis, that solid that you will get is called axisymmetric. Axisymmetric. Then you have a r equal to, for any radial line you have a plane. That plane is always in a state of plane strain if the loading also is axisymmetric. Then every plane remains wherever it is. It neither goes to the left nor to the right. Every particle remains in the same plane. It does not move out of the plane. Okay, so there are two states. So axisymmetric solid also is a problem of plane strain. Yes. The other one is plane stress problem. So, 2D plane problem, the next problem that exists is called plane stress. Now, when does this occur? And so, let us try to discuss. Just like plane strain, you have situations for plane stress. When can So, I have this is a prismatic body. Prismatic means constant cross section body. Constant prismatic means a body whose cross section does not change. So, if this is x axis, and this is y axis. This z is x, y, z will be outside. So, there is also y z plane. Now, if this cross section in the y z plane, whatever cross section it has got, it does not change with x, that is called prismatic. So, there is a length of the prismatic body along z axis. Now, I am saying z about z axis is very small, it is a thin, it is a very thin body as far as z direction is concerned. And then we shall have a so, if it is so, whatever I think I have written is thin plate of width, I mean plate, I mean see, because we do not know, this I am calling as a plate. Plate means two dimensional body, but actually it is a, so this plate that we are seeing, you know, that is section, that longitudinal section, I mean sorry, what is this face direct, what is called, I mean when you see directly a body, elevation, elevational you know, this is a like this, and so in the thickness direction is very small. So, this I am calling a plate. Now, plate of width b is loaded over the lateral surface edges by forces parallel to its faces. The plate will not deflect in z direction. Yes. So, there is, I mean do not go by the language, what is there, and then it is loaded in this direction, the way I have shown, y direction. So, this is one plane, xy plane, this body is lying in xy plane, and it is also loaded in xy plane, xy, z is perpendicular, z is with z dimension is very small, z dimension is very small. So, it is thin. So, this is, since the loads are all confined to xy plane, there is no possibility of this deflecting out of the plane. There will not be any deflection in z direction. Is it okay? Everything will be confined to xy plane. So, it is thin sheet, load in the same. Now, in that case, if it is so, then you can see that if I take a small element here, a point, and then draw a small element here, this will be subjected to any point in this, it will be sigma x, sigma y, and the shear tau equal to tau xy. Everything is in plane only. So, this and z equal to constant plane, z means this is I am talking of, this is on the edges, this is on edge constant x at x constant, this is on edge y equal to constant, is it not? These are the stresses. What about z? On z plane itself, z plane is free of any stresses. Z plane, the vertical plane like this, loads are applied here on the edges top, but this one and this one back side, these are completely free, nothing is acting there. So, z plane is free of any stresses. Since z plane is free of any stresses, so what are the stresses that act on z plane here? Yes, what are the stresses that act on z plane? Any z plane, z plane is constant, both sides, the thin sheet, it is a thin sheet which is in vertical plane xy like this, x is here, y is, loads are applied on this edge, This is my z positive plane, this could be my negative z plane, but there is nothing, it is free. So, what I have written, any constant z, z equal to a constant plus or minus, it is free of stresses everywhere. Now, so therefore, zx, zy and sigma z equal to 0. So, right from beginning, because of the nature of the physics of the problem, because of the body that exists, the way it is loaded, right in the beginning we are saying 3 stress components are 0. See, now I am starting with the word stress, I am not taking the strain, I am not uttering the word strain. So, when you are discussing plane stress, please say talk only about stress first. When you are discussing plane strain, please discuss everything in terms of strain. So, these 3 will be 0. So, this is what is shown here also, thickness. Since the distance between these faces z equal to b is very small, the above stresses can be considered. See, this is a very thin sheet. So, this surface it is 0, this surface is 0. So, how much will be the variation inside? Since thickness anyway is very small, so almost nothing. So, we can assume that these 3 stress components, that is what we consider, that they will be throughout in the, not only on the external surface, but also inside of the body. These 3 components will be 0, and such problems do occur. Beam is classic example. Beam width is very small, load is applied in the same plane either on the top or bottom, then it deflects. Beam means not 3 dimensional beam, I mean planar beam, which is confined in one plane. So, that is a case of plane stress. A wall, this vertical wall which is there of any building anywhere, it is in a state of plane stress. Okay. So, there are many situations where we have this state of stress. So, the other stresses which are not 0, the other stresses which are not 0 in the body are these 3: sigma x, sigma y, tau xy. So, non-zero stress components of these 3, and they will vary in the whole plane. They are not constant anywhere, they will be varying throughout the in xy plane. So, they will all be function of if the width b is extremely small, we can assume them to be independent of z. So, these stresses are independent of z, because nothing is changing in z direction. In b is thin, the following conditions are satisfied. So, you have these three stresses which will be function of x y, sigma z, tau zx and tau zy, and of course, their counterparts will all be 0. So, these differ from plane strain only by the condition. See, what was the plane that we considered in plane strain was xy plane, z was perpendicular, here also we have taken z perpendicular. What is the difference? There we had assumed that sigma z, epsilon z equal to 0, gamma zx equal to 0, gamma zy equal to 0. Here what we are saying, see, these stresses, these 3 are there, and then this one is 0. So, sigma z is, so in plane strain you must have noticed, plane strain sigma z is present. Yes, new times sigma x plus sigma y. but here it is not, this is. So, this difference must be understood. So, as for strains, the problem differs from that of plane strain by the fact that epsilon z is not 0 here. We have not yet put any condition on epsilon z, there epsilon z is 0. Now, epsilon z is caused by the primary stresses, because it is being pulled and pushed in xy plane. So, obviously, there will be some change in the thickness, although thickness is very small, but still it will be and plus since sigma x, sigma y and tau xy is different at different places in the xy plane. So, this quantity also epsilon z will be different at different points, because this will be, so this will be plane parallel to xy. The strain epsilon z will cause some distortion of the plane. This is what, see the fact that I am saying, see epsilon z, sigma z is 0 on the plane, z equal to constant, vertical plane sigma z is 0. Now, if you put sigma z equal to 0, you will get some strain in that direction. We will put the condition and see also. So, you will get some strain in that direction. So, epsilon, yes, there will be change in the thickness of the problem, and since sigma x and sigma y is a function of x y. So, at every point sigma x, sigma y and tau x y is different. So, this quantity also will be different, this change in thickness, that means this is strain, and therefore, there will be some undulation on the surface. It will not remain plane, whatever plane that you are seeing in front of you, elevation, after the loads are applied, theoretically it will not be plane. That is what I have written. The strain will cause some distortion of the plane faces of the plate. This is important. It will cause some distortion. Distortion means it will not remain a plane. I mean, it is true that because thickness itself is very small, this in view of small thickness itself is very small. So, this distortion also will be very small, this is true. So, what are the equations that govern this kind of behavior? So, out of 3 equilibrium equations, if you substitute or if you put the 3 stresses 0, 3 stress components are 0 here, 3 stress components are 0 here or not? How many people? 3 stress component. What are the stress component? Yes, tau zx, tau zy and sigma z 0. So, in the equilibrium equation, please put this. So, you will find that the third equation becomes 0 equal to 0. Third equation, because it has all these 3. So, third equation disappears, and the first and 2 again one term drops, and you are left only with this. So, you are left only with 2 equilibrium equations. Boundary conditions have similar form as that of plane strain. There is no change, because here also the domain is any plane, it is a domain, your domain. So, you have the boundary condition here. So, you can specify either displacement or corresponding stress. So, that remains the same. So, this is equilibrium is got. Strain displacement. These 3 will remain. will be related by this only. So, this was the same u v w, sorry, there is no w, u and v. Even the compatibility equation only one in 2 dimension, that also remains the same. However, I have written here, however, the constitutive relation means material law, we will just now see, will be different here because there in plane strain epsilon z was 0, in plane stress sigma z equal to 0. So, we will see the difference between the constitutive relation, rest of the constitutive relation. In 3 dimensional equation, please substitute this condition. In 3D constitutive relation, please substitute this, which is the condition for plane stress. And if you substitute, you will be left only with these 3. So, I think we have discussed about all the sets of equations, strain displacement, boundary conditions, equilibrium equations, constitutive relation. So, this constitutive relation, this looks different from that of plane strain. This is there, yes. So, if it is a plane stress problem, although it is a 2 dimension, but philosophy you should understand, and so constitutive relation is different. So, both plane strain and plane stress have the same basic groups of equation, they have the same except the constitutive relation. So, now we will see the constitutive relation. So, you remember we had brought in plane strain, we had brought this form after defining this in a but in the case of plane stress, actually if you take 3 dimensional strain stress relation, make sigma z, first one sigma z 0. So, you will be left only with this. Here again you will, second one you please put sigma z 0, you will be left with this 2 terms, and of course, gamma x y, this is like this, other things are not related. So, this is exactly the difference, though the form is looking same, but this here E star nu star, they mean different things. Then whatever we have discussed, I am summarizing, is the basic formulation is stress based approach. This I am giving in for both plane stress as well as for plane strain, because the only difference between these two is the constitutive relation, the rest is all same. So, we choose stresses as unknowns in a stress based, here I have said in a stress based approach, stress based, not displacement based. Displacement based is usual, you have got all the equations. So, please write down your equilibrium equations in terms of displacement, that is displacement. Now, in a stress based, what is? So, because here it is, we can derive the equation. So, I have taken it out. So, in a stress based approach, this is your compatibility equation, 1, there is only one in plane problem, 1, and please write down this in terms of stresses using constitutive relation. So, this is epsilon x equal to this in plane strain, I have just taken plane strain. So, please write down this, then similarly other So, this is the first one for plane strain if it is this. So, if you substitute it here, yes, this. Okay. So, please convert this, transform this in terms of stresses through constitutive relation. So, constitutive relation, for example, epsilon x equal to this. Similarly, epsilon y will be similar, this minus nu divided by E, this, and please find out the second derivative of epsilon s with y square. So, it is becoming this. Similarly, we have epsilon y and sorry. Okay. So, this is strain and then convert this into in terms of stress. So, second derivative of strain, because this is there in the compatibility equation. So, please write it, gamma xy in terms of stress is already there, is not much problem, and second derivative of gamma is this. Second derivative of gamma xy with respect to x and y in terms of stress, take second derivative. So, it will be same and then multiplied by this. So far we have not used, we use strain, constitutive relation and then compatibility relation in order to get these. Now, then I am saying using equilibrium equations we eliminate tau x y in the above. For example, I want to eliminate tau x y. So, I am doing this using equilibrium. Now, let us see how. So, this is your first equilibrium equation, it is like this. Therefore, I want to take out this on the left hand side and then also take a cross derivative. This is already with respect to y, I take also with respect to x. So, what you get is this will become second derivative of x here, right hand side, and this will become first derivative of bx. So, this is the first equilibrium equation. Then second equilibrium equation is this. Second equilibrium, there are only two equilibrium equations. So, second equilibrium equation is this, and here also I can get the same this one product, derivative with respect to x and y from here also, because here it is already x. So, please take about y. If you add this and this, a and b, add a and b, this and this. So, left hand side you are getting 2, right hand side you are getting first derivative, minus second derivative of this, then this is okay, and then the other one from the here b is this and this. So, I have simply added a and b. Here we had left this on the previous slide, we had this term equal to this. Now, we have got this. Now, we have got this, and this we got it by averaging, from finding out from two equilibrium equations and then averaging, because this can be found out from any of the equilibrium equations. So, what we do, we take from both and then we average it and find out this. So, this you please substitute it here, substitute it in this here, because this is there na. So, please substitute this here 2 times this, and that is what has been done here. See, this is there, this, now I am substituting this 2 times this, I am substituting the value from here which I have got, and this is what I have got. So, I am substituting it here and it looks like this. This is equal to this. So, I have used compatibility, I have used constitutive, and I have used equilibrium so far. Is it okay? So, I think in the process you must have noticed that we have got one is this is this second derivative in terms of all stress quantities, right hand side is only stress quantities, and then other one gamma x, this one is there, this is also only right hand side is all stress quantities, this is another, and there should be one more epsilon x, and second y is this. So, this is, I mean there are 3, one is this is 3 and 2 was somewhere and this is 2. Please substitute this 1, 2, 3 in your compatibility equation. Compatibility, where is compatibility? Compatibility is this. This is your compatibility equation. So, please substitute this, because this you have found out, it is this first term. Similarly, you have found out this, similarly you have found out this, all you have found out in terms of stresses. Using what? Using constitutive relation and equilibrium both. You should not forget that it can be found out only, strain can be found out only by constitutive relation in terms of stress, but that is not enough. You have to make use of equilibrium also. So, we have made use of equilibrium and constitutive relation in order to find out these values in terms of stresses, because all the 3 sets must be used. So, if you substitute it here, क्या हो गया 14, So, please substitute the above expressions in the compatibility, So, you get like this, something like, I have just substituted. So, please substitute. I mean, it is just anyway. So, this is, if you substitute and finally we get, see, everything gets cancelled. So, we are getting del square this plus this with respect to x square, del square with respect to this y square, and plus this body force terms. I have already written. So, we will get this. So, this is the compatibility equation. What is this? This is compatibility equation in terms of stresses. And now, if body forces are constant, see, if they are constant, so they will be, this one will be 0, this and this. Constant or they are not there. Even if they are constant, derivative will be 0. So, then you have del square sigma x plus sigma y equal to 0. So, stress based stress based two dimensional problem can be tackled via is it okay? Del square sigma x sigma equal to. This is also known as Levy's condition. I don't know. This is not important. Huh? So, for a plane problem, either plane stress or plane strain, you will always this condition will be satisfied. It is true of both. Either you have E star nu star or you have simply E and nu. In plane stress you will have E and nu, physical E and nu. In plane strain you will have E star nu star if you write in the same form. So, in both cases you will always get del square sigma x plus sigma y will be 0 and this condition must be satisfied in order that the problem is in state of plane stress or in plane strain. Okay. So, okay. Now, there is a very popular method, stress based method, which is called stress function approach in 2 dimension. It is also extended to 3 dimension, but 3 dimensional analysis is little complex. 2 dimension we can explain very easily. What is a stress function approach for solution of any problem? So, these are my equilibrium equations. You assume a function, because these are my equilibrium equation, you assume a function in such a way which satisfies. So, okay. So, stress function approach, you have got 2 equations of equilibrium. This is okay. I have taken it without body force for simplicity. Body force, it becomes slightly complicated. I mean, because I will have to take also that. So, I take these equations without body force. So, if I assume a function phi such that, now this function I will give the name, this function is called Airy stress, because this approach was given by Airy, AIRY. See, how to solve a plane problem, how to solve a plane stress problem or plane strain problem using stress approach, not displacement, but stress approach. It was given by, this method was developed for both plane strain and plane stress by Airy. So, Airy goes like this, he says he will express everything, these 2 equations he will express in terms of a single function phi. He will have everything in terms of a single function phi. So, he chooses a function phi such that sigma x can be found out by second derivative of that function with respect to y. I mean, this is the condition. Then sigma y is second derivative of phi with respect to x. If it is y, then it is x. If it is x, then it is y, second derivative. And if it is a tau x y or tau y x, then it is the minus del square phi, it is the cross derivative. Now, if you substitute this here, 0 equal to 0 you will get. In case this is these 3, if it is valid, and if you substitute it here in first and second equation, both are satisfied. So, equilibrium equation is identically satisfied with this kind of. So, this is called Airy stress function approach. So, there somehow you have to find out a function phi choose a function phi, then you can now I take this one whatever we have taken and write down compatibility equation in terms of stresses. Compatibility equation is in terms of strains epsilon x, epsilon y and gamma xy. Please convert that into terms of stresses, that we have already done, and then substitute this. Then substitute this and this in terms of phi. So, you will get some equation only in terms of phi. So, what is the compatibility? So, if you substitute that, when you substitute your compatibility equation gives you the del fourth phi equal to 0, biharmonic equation. So, if you can solve this, del fourth phi is a homogeneous fourth order biharmonic equation. It is called biharmonic. So, there are mathematical tools to solve this. This is a very standard problem in mathematical physics. So, methods are there to solve this. So, one can find out what are the, and once you get phi, you get stresses sigma x. Once you get phi means, yes, sigma x will be this, sigma y will be this, tau xy will be this. So, that is all. So, this was his approach of Airy. So, Airy stress function approach is assume this, you take this form satisfying the equilibrium equation, substitute in the compatibility equation and then you get this, and once you solve this then you can get the all your stress field. It can be done for simple problem, but not for any. So, Airy stress function is quite all right for some simple very ideal problems, very simple, but the moment you go to practical anything that it becomes very difficult to, because the solution of this is not easy. Displacement approach is much better. Please count the number of equations in plane strain and plane stress and number of unknowns. How many unknowns are there? Just like we have done in 3 dimension. Yes, please. 8, very good. 8. So, this is, I can add this. Yes. So, number of so, you have strain displacement relations, you have equilibrium equations and you have constitutive relation. Constitutive relation is not shown here, you already know. So, I have written here number of equations, 2 equilibrium, 2 strain, 3 strain displacement and 3 constitutive, 8, and number of unknowns, 2 displacements, 3 stresses and 3 strains, 8. So, for any 2 dimensional domain, this is your domain and this is your boundary. Boundary conditions will be given either on displacement or stresses, and you have to solve this problem as a boundary value problem, as a 2 dimensional boundary value problem. So, this becomes a 2 dimensional boundary value problem. Instead of 3 dimension, you have a complete definition of proper 2D problem. So, this much is, I hope there is nothing. So, theory wise it completes 2 dimensional 2D elasticity, and there are many practical problems which can be solved as 2D elasticity problem. How to solve? Now, I will tell you. So, this part now is goes. Here, I have tried to, some examples I have taken and tried to describe them properly. So, for example, plane stress problem, beam problem that we study. Beam problem is an approximate problem of two-dimensional plane stress problem. Two-dimensional plane stress, if you can solve, then because your beam is nothing but in two-dimensional, it has got depth, it has got length, no thickness, it is a sheet of paper, all the loads are acting in the same plane. So, it satisfies the condition of plane stress beam. So, beam looks like this in two dimension, it is supported here, and I mean boundary condition I specified at 2 points, two planes, not only 2 points, complete depth. Just like in a 3 dimension you had complete area, here it is this boundary condition. Again on the top you have the boundary condition, bottom you have the boundary condition. So, all the 4, so it is a 2D. So, there are 8 unknowns and 8 equations, and these are the top and bottom boundary conditions, that is here you can just see here x plus h by 2 load P, tau yx here na here, tau xy x h by 2 means top surface 0, is it okay, and bottom surface minus h by 2, both these are 0. So, top bottom boundary conditions are over, and then what are the boundary conditions at 0 and L. So, 0 is 1, if this is a diaphragm, if this one is a diaphragm, so this will be free to move here. So, u cannot be 0. So, what can be 0 is sigma x. So, sigma x is 0 both here as well as here, because this is also diaphragm. So, sigma x L y 0, and similarly the vertical displacement which we call W, I think in that one we call, but here since we are taking y, so vertical displacement here and here both are 0. So, this defines the completely this problem, and we can, so this is one example. For example, let us say another example. These are examples. So, these are some examples of plane stress, and so this is okay. Then another example is this, and then I will stop. A prismatic bar means just see here, under self weight, it is just from the roof it is. So, how will you solve this? By the way, you have done this in strength of material. This problem is very common problem in strength of material which we solve. I have written here stress field. What is stress field? So, only one equilibrium equation that is not satisfied is this, and this is equal to given as weight. Self weight means this body force becomes rho g. Then I think let us have a break for few minutes.